First, I will just input the code related to serial communication. I prepare until the serial communication is established and fully operational. For reference, in my specific case, when I use debugging related code, I actually use serial communication for debugging purposes. But if I find that I don't need that serial communication once it's completed, I handle it in a certain way. I write the code like this. If you run it once, you will see hello gold printed. However, if we assume that we have completed the project or are in mass production, the actual debugging related code is not needed, so I will comment these out and save them. When I reset the Arduino, now you can see that there is no output. This is because that section is not declared in the macro debug here, so we are ignoring it and moving on. The reason for this is, whether it's an Arduino or any other embedded device, it has much fewer resources compared to the general large PCs we use. So, to conserve them as much as possible, I only include such codes when debugging is absolutely necessary. Once the project is completed, or in mass production, I handle it in a way that these codes are not included. Then I remove the define comment and set define debug. If I want to see how the Arduino operates when a specific variable has a certain value, I need to inform the Arduino of this variable's value. You need to specify whether it's an integer or a decimal. For example, when controlling RGB, if I want a specific RGB value, I need to check if the Arduino can accurately represent that color on the RGB LED. Of course, I could input that color into the code each time, but that would take a long time to verify and upload. Instead, I can write the code so that the Arduino receives the RGB values in real time via serial communication and reflects those values on the RGB LED. So what you can use is something called pulseint, and I'll show you an example. Similarly, let's assume that in this particular scenario, we can observe that this is one of the debugging processes. So here we have several steps, such as if, debug, and if, which the process involves debugging and checking. And then let's assume that we are just receiving 8-bit integer values for now. Then I'll proceed to write the code in the following manner. First, I'll declare a variable named value and assign it the result of the cgear.parseInt function. After that, I'll make sure to test the code to ensure it works correctly. Finally, I'll try uploading the code to the server to see if everything functions as expected. When you upload, it initially displays Hello World. And in this state, if you input a value of 55, between 0 and 255, the Arduino converts the value I entered into an integer and puts it into value. then sends that value back. So later, when debugging, you can use the integer values you received. I have already set it to 8-bit, but if you want, you can receive them as 16-bit or 32-bit. You can use the received values for various actions, such as setting RGB values, as I mentioned earlier. Similarly, you can also receive floating point numbers, not just integers. So, you input pulse float, change the robot, and then upload it. After that, if you input 12.34, it receives the floating point number and displays it like this. Similarly, you can also receive floating point numbers in this way. And you can accept either float or double types. Continuing from what we did last time, I mentioned that we can represent numbers in decimal or hexadecimal format. For example, in this particular case, you can see how the system handles the input. Essentially, it is designed to accept and process these types of numbers efficiently. You can also set formats like the number of decimal places, disa. If I send 12.3456, again here, it will be cut off to 2 decimal places by default. If I want to see the number of decimal places for a longer period, I can input the number 4. This will display the decimal places more extensively, allowing for a clearer and more detailed view of the numerical value. You can see that 12.3456 is displayed with 4 decimal places. In this way, you can also set the decimal place format. Next, let me show you something that I often use when debugging. Here, I will use it, for instance, actually the process of completing one full loop takes approximately 2 seconds. This duration is consistent and can be observed each time the loop is executed. If you upload it this way, then in a similar manner, the values come in like this. What I want to show you now is that if I input values here, they are just simply the values in the for loop. But if it's sensor-related data values, they come in exactly like this. If you want to visually confirm something more clearly, instead of using only the serial monitor alone, there is an additional tool called Serial Plotter available as well. If you click on that option tool, it displays all of your data points in a graph format representation. Another interesting point worth mentioning here is also that if these sensor readings values happen to be from a 6-axis motion tracking sensor device system, even just considering solely the gyro-specific axis-based measurements alone would still represent 3 distinct axes. There are 3 values, right? Assuming there are 3 values, I will delete hello world. If there are 3 values to erase, the last one is processed as ln, and this allows for a CSV file in a comma-separated format. This means that each value is separated by a comma, making it easier to read and process the data. I will set this option to 60, and I will show you how it actually works. When uploaded, you can see the values coming in like this on the serial monitor. But you won't know this just by looking. The serial monitor is a tool that allows you to see the data being transmitted from your device to your computer. It is very useful for debugging and understanding how your device is working. By looking at the serial monitor, you can see the exact values being transmitted, which can help you identify any issues or errors in your code. The CSV format, which stands for comma-separated values, is now separated by commas. This means that each value in the dataset is divided by a comma, making it easier to read and process the data. If you look at this format in the Flutter framework, you can visualize the data in a graphical representation like this. Moreover, another thing I can do here is that the order I sent you is XYZ. It's an accelerometer, which is a device that measures acceleration. If we assume it like this, we can use the serial print function to send XYZ in 3 dimensions and then receive it back. When you open the Flutter application, you will immediately notice various labels that are clearly marked as X, Y, and Z. These labels represent different axes or dimensions within the interface, providing you with a structured way to navigate and interact with the app's features. At first, it got disconnected and then uploaded, but you can send this initially to specify the header name, which is crucial for the process to ensure proper identification and functionality. You should check the sensor values in a way similar to this, or check certain values on the Arduino side. Naturally, you need to include serial print statements at each interval to verify the basic functionality. When debugging, you just do it, regardless of the amount of code or anything like that. And later, the debugging code is going to get really extensive, right? Then it can take up a lot of code and potentially affect the actual program. So at that time, you can comment out this code to deactivate all the debugging code. This is how debugging is done. In this session, we practiced debugging Arduino using serial communication. I haven't decided yet what content to cover next time, but I will prepare something related to Arduino or other hardware. Well then, I'll see you next time.